Hi class, welcome to the next section, chapter 12.4. Today we're going to talk about calculus on our polar coordinate systems. So, similar to how we did it for the parametric curves, I'm just going to kind of go through the formulas and then we'll go through an example of each. Remember that these polar equations that we have are just parameterized curves where x is our cosine theta and y is our sine theta, right? So the forms still work the same way. My dy dx follows the same formula that I had from the calculus on parametric curves. So I'm going to differentiate differentiate y with respect to theta and throw that on top of the derivative of x with respect to theta, right? So x is r cosine theta. R, remember, is a function of theta. So my x is defined by my function value times cosine theta. Similar for my y values, right? So r sine theta is r, which is given by a function, times sine theta. So dy dx is y prime in terms of theta divided by x prime in terms of theta. And so I'm going to differentiate first. I think I do y. And so this is the product, right? So this is going to follow the product rule. This is going to follow the product rule. So on top, I'm going to have f prime times sine theta, right? Plus f times cosine theta, right? So here I just kind of left it standard with the r instead of the f thetas, but r and f of theta is the same thing, right? So I can replace them as I see fit. So again, this is just r prime is my derivative of r with respect to theta. Okay. On the bottom, I'm doing the x's, right? So it's the same thing. Um, f prime of theta or r prime times cosine. And then it's going to be f times the derivative of cosine, which is negative sine. So that's why the negative is on the bottom here. And if I want to replace these r's with the f form, I can do that. So whichever one you're more comfortable with, if you're just like, oh, r is by this function, and you want to use that, you can do that. If you like this form of the formula, you can just use this as well. Doesn't really matter, right? They're identical, which is why there's an equal sign here. Okay. So now for me, yes, that's my formula here. Okay. For area, it's going to be similar to what we had for the parameterized curves, except for the parameterized curves, we just use sort of a substitution based off of integration by parts. Now we didn't derive, I just kind of said, hey, this is where this comes from. And I kind of just did some hand waving there. I said, if you want to look more into it, do it on your own. For area here, for polar curves, we're going to actually have to dig in a little bit and actually derive the formulas a bit. So let's recall that the area of a sector of a circle is given by 1/2 theta r squared. And this should make sense to you because when I have the entire circle, my angle is 2 pi, right? And so 1/2 times 2 pi r squared gives me pi r squared, which is the area of a circle. So you can always just remember pi r squared is half of 2 pi r squared. So for any area of a sector of a circle, piece of a circle, right? You're just going to use that area, or I'm sorry, that angle that spans that sector that you're interested in. Okay, so it's half of the angle of interest times the radius squared is your area, right? And so that is nice, but that's not necessarily what we need for r equals f of theta, right? And I'm not just gonna substitute in here. Well, I kind of am. So let's say that instead of r, right, standard radius, my radius changes as the angle changes, right? Which is why we get these cool polar curves that we have. So I now have a variable radius curve, a sector of one, right? This isn't going through all of 2 pi or even from 0 up to amount. It's from some angle to some angle, right? Which we call from alpha is the start angle and then beta is the ending angle, right? And that's that angle measure I have in between here of theta, okay? So what we're going to do is we're going to break this sector, right, into infinitely small slices like we normally do. Um, so instead of taking slices of the area under the curve, I'm taking slices of angles along here. Okay. So each of them have an angle measure of delta theta. So ith slice, remember the ith slice is just some random slice, is going to have an area of 1/2 f at that angle measure, right? Theta I squared times delta theta. And so if we add up the sums of all of those and take the limit as it goes to infinity, um, it's going to be the sum of all of these delta i's, right? These theta i's. And so as n goes to infinity, it turns into the integral from alpha to beta of 1/2 f theta squared times d theta. So remember, this is not a derivative, it's not second derivative, it is squaring the function. And it's from alpha to beta, my angles of interest, right? So if we need to find the area between two curves, A2 minus A1, just the standardized way of doing it. I find the area of A2, I subtract from that the area of A1 specified by F2, right? Second function, F1, the first function. And remember what we could do, the law of integrals says that we can write this all as one integral instead of two integrals. So I could just square those two functions and subtract them and be on my way, or think of it as a difference of squares as well. There may be times where that helps, um, but most of the time, just square both functions and subtract them, and you're okay, right? For arc length, so remember this is the length around the curve, right? So in chapter 12.2, we had the arc length for a parametric equation was from A to B, x prime with respect to t squared plus the derivative of y with respect to t squared added and the square rooted, right? That was for arc length. So since we're in polar coordinates, we are still parameterized, right? It's just different. We have theta now. And so we can rewrite this as x prime theta squared plus y prime theta squared, add them, take the square root. There's really no derivations that we have to go through because they are the same thing. Okay. Um, we have the radius. If we don't have x prime and y prime, um, right? Let's say we have a function. So if you notice what I've been doing is I've been writing things in terms of the function, right? So I'm given this function, so I'm not using x and y, the parameterized versions of x and y. I'm using the function everywhere. My function, my function, my function, my function. I'm using this y prime, x prime stuff in order to figure out what extra stuff I need, the sine theta, cosine theta stuff. But everything is in terms of my function, not in terms of r sine theta, right? Well, it is r sine theta, but I'm using my function here. For area, my area formula is based on the function I'm given as well, okay? Even for the difference of area. So for arc length, it doesn't make sense to use this form because I didn't have to parameterize my function myself, right, or figure out what that looks like, and then be able to do the math, which is a lot of work, and we already don't like to work a lot here, right? In a math class, ideally, I choose the fastest way for everything possible, but not going fast, right? Just want to do less work. So I would like to do this in terms of r and f theta. So I know what this looks like, right? X prime theta and y prime theta. I did that here, right? I have a y prime theta and an x prime theta. So what I'm gonna do is I'm gonna see if I plug this stuff in for the general forms that I have, if I can make my life a little bit easier. Okay. So here my function is r equals f of theta. Again, I'm going from alpha to beta. Um, so let's write it as a polar curve instead of as the parameterizations. So I know x naught is r cosine theta, and I'm sorry, x theta. So I can rewrite it this way, and then y theta is r sine theta or f of theta sine theta, right? So I'm going to go ahead and plug everything in. So let's find these derivatives one more time real quick, just so that we're clear what we have. Um, Product rule gives me this for x prime of theta, and y prime of theta is given to me for this. Again, I can replace r with f theta. I can replace r prime with f prime theta if I need to. I will anyways. They're equal, right? It's just the way that I want to call it. So substituting that in for what we have here. So first, let's go ahead and square this. So I'm going to get r prime squared cosine squared, okay, theta. Remember, when I square a binomial, I multiply these things together and multiply times 2. So I'm going to have 2r prime cosine sine, 2r prime cosine sine. And then I square the last term, so that'll be plus r squared sine squared. Okay. And then I add to that the same thing here. So r prime squared sine squared, 2r prime sine cosine. Okay. And then the last term, I just square it and add it to it. So that's r squared cosine squared. And so from here, this is everything that would be under the square root sign. So I'm going to go ahead and simplify this and see if I can get something a little bit better. Okay, and so before I move to this next part, basically all I'm going to do is, you see here I have the r prime squared alone. There's no other r prime squared alones except for here. So there's a cosine and a sine term for that, right? That doesn't show up again. So r prime squared, cosine squared, sine squared. That's nice because that's going to turn into 1. Okay, I have the same thing for r squared. All right, I have an r squared cosine squared, r squared sine squared. So that would be next. That's nice because this will go to 1 also. And oops, and then for the stuff that's left, well, this is a 2r prime cosine sine. This is a 2r prime cosine sine. So identical but opposite in sign. And so those two cancel out, and then the other two, the other 4, they pair up and they factor with each other, right? So there's 2, that's the 4, and then the rest of it canceled. So I know this is going to go 1, this is going to go to 1, so I have r prime squared plus r squared. And there's not really much more for me to reduce that, right? So I can replace that now as alpha to beta instead of, so again, I'm writing r squared as f prime and r squared as my function squared. So I can now replace my formula in terms of what I actually have, right? So I don't have the, r cosine theta. I'd have to pull that apart first in order to do that. So I'm given a function. I can now just use that function in my formula and get straight to calculating the arc length. Okay, so let's go ahead and do an example. So find the equation of the tangent line to r equals 2 sine 3 theta, right? So if you remember, this is a rose, okay? And we want to know what the tangent line is at theta equals pi over 4. Okay, so everything is given to me in polar coordinates. I'm going to do my work in polar coordinates. It's a lot more work to go ahead and change this into rectangular coordinates and then try to figure out everything. So we're just going to work on it as is. So remember, dy dx is the same thing as me just dividing the numerator and denominator by d theta. Okay, so now I have the derivative of y with respect to theta over the derivative of x with respect to theta. And so I'm going to use my function, right, r. So r prime sine theta, my function r cosine theta, and then my denominator. Okay, so I did the work for this already. So now I just got to actually find these values. So first thing I need is to find the derivative of r, okay, with respect to theta. So I'm really just going to differentiate this with respect to theta. So I'll have 2 cosine, and then chain rule says I'll have a 3, so this should be 6 cosine 3 theta. Okay, so r prime sine theta. So my r prime is 6 cosine 3 theta, and then sine theta. Okay, plus just my r times my cosine. And then on the denominator, I'll have 6 cosine 3 theta again, but times cosine. Okay, and then minus my r function, 2 sine 3 theta times sine. Okay. So pretty straightforward. So now if I want to know what this derivative is, I just plug in pi over 4 everywhere. I think I did this a little differently, and I look at r and r prime separate, which is fine. It's really the same amount of work. So pi over 4 here gives me actually 3 pi over 4. Okay, and so sine 3 pi over 4. So this means that if you have your unit circle handy, then that's great. This is less than pi, right? So this is the pi over 4 equivalent in quadrant 2, right? So for sine, this is a positive value in sine because I haven't hit the other side of the x-axis yet. So this is going to be root 2 over 2 times 2 gives me just root 2. Okay. R prime, okay, so that's the 6 cosine 3 theta. So it's going to be the same angle, right? 3 pi over 4. So that's still going to be root 2 over 2, but it'll be negative because it's the cosine value. Okay. And so it'll be 6 over 2 times root 2 negative. And so that's a negative 3 root 2. Okay. Because the 6 over 2 cancels to a 3, and I'm negative because it's in the second quadrant. Right? So it's on the negative side. So now that I know R and R prime, I could have just put pi over 4 everywhere here, but now I can just replace pi over 4 everywhere, and everywhere I see R and R theta, I can just replace the values. So looking at the derivative at theta, or at pi over 4, I'm sorry, for this one is going to be root 2 times sine pi over 4, which is root 2 over 2. So 3 root 2 times root 2 over 2 plus, and so this is root 2 times root 2 over 2. Okay, and in the denominator, r prime, so negative 3 root 2 cosine gives me root 2 over 2. Okay, and on the bottom, I have negative, I'm sorry, minus this I know is my r, right? So that's root 2 times root 2 over 2. And so here we can do some quick math. So every time I have a root times a root, that's just 2. And then cancels the bottom. So this will be negative 3 plus 1. This will be negative 3. And this will be minus 1. So negative 3 plus 1 on top, negative 3 minus 1. So negative 2 over negative 4. And so that gives me a positive 1/2. So at the angle pi over 4, the rate of change of my function, r equals 2 sine 3 theta, is 1/2. Okay. So now looking at what do I get for x and y out of that, right? Out of my points, because I have the rate of change, but I also need the point that it goes with. Uh, I can do that here, but the problem is that the point I get is the rate, it's in polar coordinates, and the tangent line that I'm going to find in would need to be in polar coordinates as well. And it's too much brain power, so I'm just going to go into rectangular coordinates. So for x, this is root 2 over 2. R we saw is root 2. Okay, so we know that turns into 1. And for y, this is negative 3 root 2 times root over 2. Okay. Oh, r is root 2, sorry. And so I get the same thing. Okay, 1, 1. Y equals mx plus b at theta gives us so far rate of change of 1/2 at the point 1, 1. So y equals mx plus b. So x and y is 1, m is 1/2. So this is 1 equals 1/2 plus b, so b equals 1/2. Okay, when I subtract 1/2 on both sides. So my slope then is y, or my tangent line is y equals 1/2 x plus 1/2 is the tangent line to r equals 2 sine 3 theta at theta equals pi over 4. Back here in Desmos, you see we have our 3 petal rows. We have our tangent line at the point 1, 1 for our curve for our rows, right? So that's what this would look like. And so um, that's nice and everything to have this, but it's kind of conflicting, right? We have rectangular coordinate equation and a polar equation. So my tangent line is in polar, or I'm sorry, in rectangular, and then my polar equation is, it's polar equation. So let's go ahead and turn this into a polar equation. That way, we're not kind of mixing up our our uh, our coordinate systems. Back here in the presentation, let's go ahead and write the tangent line in polar coordinates. So for y, we would have r sine theta. My m is still 1/2. My b is still 1/2, but my x, I guess I should refer here. My x is r cosine theta. R sine theta. So we know what r is. R is a function here, 2 sine 3 theta. For r here, we're going to use the standard value for r. Because we're not using our function anymore, right? We're just having some r. So our goal is to get everything on one side and r on the other side. So first thing I'll do is I'll subtract this 1/2 r cosine theta, okay? And then from here, pull out the common r. Now divide this to both sides. Now I have 1/2 divided by sine theta minus 1/2. And then let's just go ahead and move this 2 to the bottom. So this will be 2 sine theta, and the 2 will cancel with this 1/2. Okay. So now I have 1 over 2 sine theta minus cosine theta. And so this would be my equation in polar coordinates. So here you can say all I've done was added my line. You can see it's blue. It's right on top of the green line. Okay, the green line was my tangent line. Turn that off, turn this on, turn this on top. I guess I can't put it on top. It's all about the order. If I move this here first and I turn this on, then the green should be the one that comes on second. Maybe it's a color thing. Anyways, you can tell that these are on the same line. Okay, so this is my tangent line in rectangular, and this is the tangent line in polar coordinates. So on for another example. Find the area enclosed by r equals root of 1 plus cosine squared 5 theta. Okay, so our formula is that the area is from alpha to beta, 1/2, and then my function squared, which is nice because this is a square root function. So now the question is, well, what's alpha and beta, right? So we'll just go to be safe from 0 to pi. It'd be nice to graph this first and kind of look at what it looks like and see, play around with the angles that I need to draw the whole thing. But I did that before I started this example. So from 0 to pi, it gives us this entire graph. So I'm just going to square it, right? So I square my function. I have my 1/2. This is much nicer. I can pull this to the outside, make a u substitution here, okay, for 5 theta. So du 5 d theta turns into 1/5 du d theta. And so then we just go ahead and sub all that back in, right? So my 1/2, and then this will be 1/2 um, cosine squared of u du. And then I can use the reduction formula. So this will turn into 1/2 plus 1/2 cosine plus cosine 2u. Okay, it is 1/2, and we factor that out for the 1 over 20 here. That's why this changed. And so now we can just integrate. Okay, so this goes to 1/2 theta from 2 pi to 0. This here is, I'm in u now. Okay, so that's why I keep this thetas here to remind me to go back. And then we know that this is 1/2 sine 2u. Okay, and then there's a 120 here as well. Okay, and so the 1/2 made that 140 from 2 pi to 0. And we resubstitute in our 5 theta for u. Then we can just evaluate everything, right? The nice thing is at 0, this goes away, this goes away. At 2 pi and at 0, this goes away. Okay, because whenever sine hits the um, you know, 0 pi, 2 pi, I always get out 0 for sine. So this whole thing disappears. And I just have to plug in 1/2 at 2 pi. So this will be a pi. And then this will be 10 pi over 20. So that'll be 1/2 pi as well. Okay. Add those together and we get 3/2 pi. Do another example now. So let's find the area inside of r equals 3 cosine theta and outside of r equals 1 plus cosine theta. So again, we would need to do some work here. I square one function, subtracting that the square of the other function. Obviously, I need to figure out those points of intersection so I know from what angle to what angle. So first thing first is we have to find out the points of intersection. So we set these two functions equal, right? My first function, 3 cosine theta, is equal to 1 plus cosine theta. I also have to know which one is larger, so I know which one is the outside function, although here it's rather easy to tell. This has a radius of 1, this has a radius of 3, so I'm pretty sure this is the larger function most of the time, which is why I need to know when the intersection happens. This is definitely larger starting off than this is, right? This starts off at 3 for cosine of 0. This starts off at 1 at cosine of 0. So I know that this is the larger function. So so I'll find my 2 points and the interval that contains 0. I know that this is when it's larger. Um, and then I can always check, right, values in between the points that I find to find out if there's other times when this first function is larger. Okay, I set these equal to each other. I'm gonna combine my cosines. I'm just gonna move everything over really. So I like to always move things to where they say positive. So I move cosine n1 over. Then I can actually didn't need to do that. That's probably more work than I needed. I should have just subtracted cosine, and then now I'm gonna bring the 1 and the 2 over. So this is gonna be cosine theta equals 1/2. Okay, and we know when that is. So this is a 30, 60, 90 triangle. And the smaller side is the one that needs to give me the 1/2. So that means that cosine, the x-axis is the small side. So it opens up for y being larger. So that means this has to be a 60-degree triangle. So this cosine theta here works when theta equals 60 degrees or pi over 3. Okay. And so if you don't remember, again, use your unit circle in order to point that out. But the range for this, okay, for the inverse part, or the domain, I don't remember, is that the angle has to be between negative pi over 2 and pi over 2. So we're staying on the right-hand side of our graph, right, quadrants 1 and 4. So when we put this together, I have negative pi over 3 to pi over 3, 1/2 my first function squared, 3 squared is 9, cosine squared, minus my second function squared. And so I'm going to have to expand this. So I have 9 cosine theta. And here I'll just do the perfect square. So I'll have, let's see here, 1 squared, 1 times cosine times 2, right? And then cosine squared. And I have to distribute this negative. So inside here, everything is positive. So with this negative on the outside, it all turns to negative. I can combine terms with these cosine squares. So this will be 8 cosine squared. Okay. And I can move this -1 to the outside. I can't necessarily factor for, no, it doesn't factor, right? So I can't make this a perfect square. So what I'll do, I just separate it and integrate. Cosine squared, we use the half angle formula on. So this will be 1 plus, 1/2 plus 1/2 cosine 2 theta times the 8. So that'll turn all those into 4s. And then with this 1/2 out there, it'll actually turn it all into 2. So we can go ahead and do that. So we'll make this reduction here. 2 cosine we can integrate just fine. 1 we can integrate just fine. So we'll go ahead and start to add like terms, right? 4 times the 1 minus the 1 is the 3. There's a 4 here, a 2. I can use this u equals 2 theta substitution, which we do all the time. So we can just kind of bypass that. 1/2, 3 times theta. This will be a 1/2. So this will turn into 2 times, well, we'll just leave it 2 here. 2 sine 2 theta. This will be minus the sine theta. Okay, the 2 in front. And we will evaluate, oh, yeah, that should be it. And then we should evaluate from pi over 3 to negative pi over 3. We can go ahead and distribute this 1/2 in as well, or we can pull out a common 2 here, which will bump this up to a 6. Doesn't really matter. We'll just go ahead and throw this in. So what we're doing here is we're using symmetry, and we can just take this 1/2 away, and then we can just go from pi over 3 to 0. Again, knowing what our graph looks like will help us a lot. If I know that the areas are symmetric from this point to this point, it makes it a lot easier for me to say, hey, this is the way it works. I can also figure that out without looking at the graph. by knowing how sine works and how an angle works, right? So 3 theta and 3 negative theta will be the same value. So there's symmetry across that polar axis there. And the way that sine works, um, even with the rows, we'll have symmetry there as well. So in the individual parts, we have symmetry. So that's how I know that I can just do half of that, right? So if you think about the graph of sine from negative pi over 3 to pi over 3, you have the negative part and the positive part, which basically just cancels each other out. So we can just look at one side and double it instead. Okay. So now that we have that, we know that when we look at sine at 0, this starts at all of these are 0, 0, 0, 0, 0. So I just have to plug in pi over 3. So the first one will give me just pi. This will be 2 pi over 3. So I believe that's similar to a 60-degree angle. So that should be root 3 over 2 times the 2. And then here, pi over 3 is a 60-degree angle. So that's the same thing again. Okay, which is nice because I have the positive and the negative form, so those cancel. Those 3 cancel, and I'm left with pi. Okay, let's go ahead and just for the sake of argument, look at our graph because if I did that at the beginning, maybe this would have been easier to follow, but again, knowing the properties of sine and cosine are very important, especially if you have symmetric bounds. It's nice to know when you can double something or cut it in half or whatever the case is. Okay, so let's go ahead and look at this graph real fast. So if you look here, um, this is the larger function, the 3 cosine theta, and then my 1 plus cosine theta is here on the inside. I have my points of intersection, which do not work as well in graphs like this. But I knew that they were at, um, these are hard to do, pi over 3 and negative pi over 3. So what do we get? Let's just plug one of these in. So is that, it's cosine, so 3 halves. And the angle doesn't work very well. Um, let's see here. I don't even have to try to find this point. So when I Desmos defaults to rectangular coordinates. I'm sure there's a way for me to put in coordinates, points, and plot them here without having to transform them, but I don't really feel like dealing with it. So a nicer way to do this is to just notice that this intersection point here is at pi over 3, okay? And the other intersection point is here at negative pi over 3 or 5 pi over 3, okay? So that's how I know. The green function is the larger function from that angle sweeping out to that angle, right? From this angle to this angle. So that's the only time when it's larger. And if you look at the symmetry along this polar axis, the top and the bottom halves are identical. So I don't need to do the whole thing. I can do just from 0 to pi over 3 and then double it and I get that area. So knowing my graph ahead of time as well, also knowing how sines and angles work and the symmetries inherent in them are also very, very helpful. Okay, and we're back. So next we have an example. So let's find the arc length of r equals 2 cosine theta for theta between 0 and pi. Okay, so here in order to find the arc length, we go from alpha to beta, which is 0 and pi. And I'm going to take my function, I'm going to square it, and I'll add to that its derivative squared. So r prime cosine starts with a c, so it changes sign when I take the derivative. So it goes to a negative sine theta. The 2 stays there. Um, so then the rest of it is very easy to do, right? So squaring my function gives me 4 cosine squared, and the derivative gives me 4 sine squared, which is nice. If I pull out this 4, okay, I guess I skipped a step there, but pull out the 4, cosine squared, sine squared is 1. Then I have just square root of 4, which is 2. And I integrate that from 0 to pi, so I get 2 theta. So that is just 2 pi. Okay, let's see. And so we know what this looks like, cosine, so it's somewhat of a circle on the positive cosine direction with an inner radius. Can't see me, but I'm doing air quotes of 2. And that is how we do calculus on uh, polar equations. So I'll see you guys in the next video for conic sections. Again, I'll remind you now and I'll remind you then that in my pre-calculus section, I have 4 videos, I believe, on conics, and I've pretty much just condensed them into one video. So if you're familiar with conics already, then the video should be enough to get you through it, you know, review the things that we're doing. If you're not familiar with conics, again, conics are circles, parabolas, ellipses, hyperbolas. If you're not very familiar on those things, I suggest you look at the pre-calculus stuff first. Um, I don't remember what chapter it is. I think it's chapter 12 in the pre-calculus text that I wrote for my pre-calc class. But it goes more in depth. There's more examples than what we'll go over in the next video. So just a heads up. Thanks, guys. See you on the next one.